Okay, Dr. Matthew J. Trom here. I'm going to solve a mechanics and materials homework problem for you. What we have is two W4 by 13 rolled sections welded together as shown. We know that for the steel alloy used that the yield stress is 58 KSI, and we're using a factor of safety of 3.0. We're asked to determine the largest couple that can be applied when the assembly is bent in the Z direction. And we've got this let's use blue here. We've got this figure here. So we're basically bending around the Z direction. Now, when I solve these problems, I always like to have a plan of attack in advance. So I'm not just writing down a bunch of random equations. I kind of want to see where I'm going. So here's kind of my plan to solve this guy. So ultimately where I'm going is that I know from the foundations of the class that the stress is equal to the bending moment couple times the value C, which is a distance, divided by I. So that's the kind of foundational equation that I'm going to use. And I also know that the allowable stress is equal to the maximum couple multiplied by C divided by I of this body rotated about the Z axis. So let's call it that. So I can then rewrite this for this couple, which is what I'm solving for, right? That's determine the largest couple that can be applied. Okay, so that's what I'm solving for. So let's solve for that guy. So M max is equal to the allowable stress multiplied by IZ, where IZ is the Z of this body, over this value C. And that is kind of the big picture equation that I'm going for. So my plan is to sort out an equation for this guy, an equation for this guy, and a value for this guy. And once I have all three of those, I can plug them back in and I can move forward. So let's start out with the allowable stress. So the allowable stress is just the yield stress divided by the factor of safety. And all of that information is given, right? So my yield stress, 58 KSI for steel, and my factor of safety is 3.0. So I end up with doing the math there, 19.33 KSI is my maximum allowable stress. So that is that. So we got one sorted out. The second piece that I have to sort out is what is this I value, this I sub Z? And we're told that we have two W4 by 13 rolled sections, and we're given in the problem statement Appendix C from the textbook, and I've basically simplified it here. There's this big table with all these different values representing different I-beam shapes, and I've eliminated all that and just isolated the one line that we actually need. It happens to be at the bottom of that figure of that appendix, but that's the value that we need, right? W4 by 13. And what I'm looking for again is IZ, which is the I for these two I-beams. Now there's sort of welded together, so there's kind of two little weirdnesses here that I need to manage. The first one is I've got two of these, one, two welded together, right? So it's not a conventional I-beam shape. And then the second is that this guy is basically rotated 90 degrees, right? So if you look at the way that the table is set up, it's set up for an I-beam in the shape of an I, and we basically rotated this guy 90 degrees to get to this guy, which is now the shape of the letter H, and there's two of them welded together. And so I've got to work out when they're talking about a moment around or a couple around the Z-axis or bending around the Z-axis in this figure, what does that mean relative to this chart and this figure? And so what I'm looking here is I've got, let me just redraw one of these by itself. So I've got one of these I-beams, I've got it all by itself, like so. And in this case, the axis that is related to what's happening in the table here, that is in the same direction as the axis in this figure, is this one y, right? So if I take this and I redraw it, basically 90 degrees rotated, this is capital Y, capital Y. And where I'm going with this is recognizing that because these two I-beams are welded together, they're basically symmetrical about this Z-axis. And so ultimately what I'm looking for, if I call this section BB, is that's my line of symmetry, right? So I basically got to do two things here. I've got to first figure out how to translate this chart into a 90-degree rotated version of it to get here. And then I've got to figure out what happens if I weld two of these together along this line BB on this plane of symmetry. So I'm basically doing those two things simultaneously as I'm solving for. Remember, it's IZ is what I'm solving for here in this second piece of it. So let's grab the key information that we need. We're not going to worry about the XX axis because remember, this is the YY axis that we're talking about. So we're going to use this guy. And we are interested in the fourth moment of inertia, this guy. So we're going to take 3.68 inches to the fourth as one of our important values. And then we're also going to ultimately need to use the parallel axis theorem, right? Because the I value for this I-beam tipped on its side like this is about axis YY, and we need to move down to axis BB. And so we're going to need some information that helps us out in terms of solving for the parallel axis theorem. So let's just remember what the parallel axis theorem is. So we're going to try to figure out I of B. We'll call this I of BB for this guy tipped on its side. And what that is just I of Y, right? So, or let's call it I of YY, right, which is this guy, and then moved by this distance, which let's just call that D1. So this distance is D1. Down to this plane where that weld line is. So it's going to be IYY plus the area of this guy times what I've called D1 squared. So that's my parallel axis theorem. Parallel axis theorem. And in order to solve that, I need this IYY, which I've got here, and then I need the area of this whole thing, which is here. So that's my area. And then I need this D1. So what in the heck is this D1? Well, it's basically half the distance of the height of this guy from Y to B, which over here, if I look very, very closely, that's BF over 2. So I'm actually looking for that dimension BF. Aha, there it is. BF, BF. And so D1 is just BF over 2, right? Because that's this distance divided by 2 gets me from here to here, which is that same distance that I've called D1, which is from here to here on this guy that's tilted over. So now I've got all those pieces of information, and I can write out my parallel axis theorem and get the value for I sub Z. So let's move to the next slide and do that. So just remembering that parallel axis theorem IBB is equal to IY. I'm just copying down what I wrote on the previous slide, plus AD squared, and IYY, remember, is 3.86. There we go. And that area A is 3.833. And then what's this D value? Well, let's go back and remember that the D value is BF over 2. So it's 4.06 divided by 2, right? 4.06 divided by 2, and that's all squared. And so if I run through and get the ultimate result for that, that's 19.643, and this is going to be inches to the 4th power. Now, I'm not done yet, right? Because all that I've done with IBB is I've sorted out the I value for just one of these two H's, right? By basically doing the parallel axis theorem to move the axis of rotation from this plane that crosses through the middle of one of these I-beams down to what I call plane BB, where that weld joint is. I've got this whole other I-beam down here, right? That's welded on. But now my life is a little bit simpler because there's symmetry here, right? So the I-beam on the top and the I-beam on the bottom are symmetrical across this plane Z, which I've called BB here. And so I don't need to use the parallel axis theorem again or anything else. I can just simply add this IBB from the top with another IBB that's identical from the bottom, and that gives me IZ. So IZ is just equal to 2 IBB, and that works out to be 39.286 cubic inches. So doing pretty good here. If we go back to the previous slide, remember we found this allowable stress. We've now found IZ, and the final thing that we're looking for is C. And so what's C? Well, C is the distance from where I'm actually doing the bending, which is in this case my plane BB, all the way up to one of the extreme edges, right? So, and it doesn't really matter which one. So it's either all the way up there or all the way down there. In this chart, it's that distance. And so if I go back over here and look at what that distance is, that's just B sub F, right? That's the distance from here to here, because again, this is just rotated 90 degrees to get it over here. So that's just 4.06. So that gives me the value for C. And now I've got all the pieces. I can put it all together. So if we go back here, let me grab this guy and move him here. Okay. So here's the equation that I'm going for, right? And I've got all the pieces. So my maximum allowable shear, remember, is 19.33 KSI. My I value, which I had to fight through some geometry to get it, but it's 39.286. 39.286 inches to the 4th. And then that C value was 4.06 inches. And if I go through and calculate all these values, put them all together, multiplication, I end up with 187.1 kips multiplied by inches is my maximum couple that I can put on that particular shape. So that's the answer to that one. Thanks for your time and attention.